Okay, welcome you all to this class. In the last class, we learnt about the AC response for R resistance, inductor, and capacitance when they are connected individually into the circuit. Today we are going to see what would happen if an RLC are connected in series to an AC source. Okay, in the next class we will see RLC parallel. So today we will restrict R, L and C being connected in series to an AC source and see what's going to happen. This is an inductor, at a capacitor and a resistance which is connected to an source. Now here the source is V sin omega t. So the when we apply a sinusoidal signal voltage, the current also would flow in a sinusoidal manner. So the shape of the waveform will be retained out here. Only thing is unlike an inductor, in a pure inductor the current would not lag by 90, or unlike an pure capacitor, the current in a capacitor we saw the current would lead by 90 degree, and a resistance it will follow the applied voltage. There won't be any phase difference between the current and voltage. So when you have an RLC combination, the current would be like something like this, which is shown in the blue line. It could lag or it could lead depending on what is the which offers greater impedance. Okay, and that too at a given frequency. Now we know that L and C they are frequency dependent components, right? So at a given frequency it is possible that the current could be leading, and at another frequency it is possible that the current could be lagging. Okay, so we'll see into that. So here if you see here, this is the vector phase diagram. Here it is, since it is sin t we have applied the applied voltage, so that will be vertically up. Okay, the V sin omega t will be vertically up. So we are assuming that there is a phase lag between the current and the voltage. So we have taken this omega t minus phi, a current somewhere here, okay, somewhere around 45 degrees. So just an assumption, it would be like, if it is like this, then what happens? Okay, now I can plot the voltage across the resistor, which will be in phase of the current, because if it is the same current which is flowing in all the three components, coming from the source and flowing through all the three components, so the voltage which will be there across the resistance have to be in phase with the current, because in a resistance we know the current and voltage they remain in phase. So we can draw a line represented by this red line VR, which is the voltage across the resistance. And we also know that the voltage across the inductor always leads the current by 90 degree. So it will be I0 L omega and then 90 degree. So we have drawn here one line VL here. Okay, so this is VL, which is at 90 degree. The current lags the voltage by 90 degree, or other way around. For an inductor we can say the voltage leads the current by 90 degrees. So at 90 degree we have drawn L out here. Now similarly the voltage across the capacitor will lag the current by 90 degrees. So the voltage across the capacitor will be VC. Now if we apply a normal loop equation, or the Kirchhoff's voltage law, so the sum of these three voltages has to be the applied voltage, right? So if you see this VL and VC, they are opposing each other. So in this particular case we are assuming that VL is going to be greater than VC. So the net direction of the voltage will be towards I can say towards northwest, like towards L. Okay, they get subtracted, and then when you take an again a vector addition of that difference signal with VR, you will get a signal which is in the top direction, which is our applied signal V sin omega t. So this is how the signals gets placed in the vector diagram. You will have I0 which is not necessarily in the same direction of the applied voltage. Okay, there will be a phase difference, and then the voltage across the resistance will be parallel to the I0, whereas the voltage across the capacitor will be 90° lagging, and the voltage across the inductor will be 90° leading, and the sum of these three voltages will be the applied voltage. Okay. So if I want to find out what is the lag, okay, from the applied signal, okay, so if you see from these vector diagrams, I can say VL minus Vx by VR will give me the lag, this angle. Okay, this angle, if you see, this is a triangle, right? If you and what is going to be this distance, this is going to be a component of V, or I can take this triangle, because I am going to add these two, right? So this is going to be a VR, a VL minus and a VC, and this is going to be VR, and then I am going to take a sum. So I am going to get this angle. So that is VL minus VC divided by R. So I can substitute by I0 XL and I0 XC and R. So I get an tan inverse, the phase difference between the current and the voltage, XL minus XR by R. Now if you see this in this particular case, if we assume that XL is larger than XC, then you will find phi is positive. That means, okay, that is the current is going to lag, okay, because it is minus phi here, so that is why it is going to lag out here. And in case XC is greater than XL, then the current is going to lead the voltage. Okay, so this is the formula which we are going to use to find out the phase difference between the applied voltage and the current. Okay, so these three components are now also we'll see. I'll show up the next slide, where this phi is dependent on the frequency also, because XL and XC are frequency dependent components. Okay, and the net voltage will be given by this vector sum of all the three voltages, VR square plus VL minus square root of VR square plus VL minus VC the whole square. Okay, so or since it's the same current which is passing through all the three components, I can take out an I0 separately. I can write, and then I can write a square root of R square plus XL minus XC. So this is the net impedance which will be offered by the three components in series, R square plus XL minus XC the whole square. So this magnitude will define the value of the current I0 for an applied voltage V0. Okay. So this is what the impedance is. Z is equal to square root of R square plus XL minus XC square. Okay, now if you see the variation of magnitude of phase and current with frequency, so this is a very important diagram to understand. So initially if you see, let me put that equation here. Yeah, this is the impedance equation, right? So initially when the frequency is 0, right? So what is the net impedance out here? So this is going to be say when the impedance is this is going to be L omega is going to be 0, right? This is going to be 0, whereas XC, that is 1 by C omega, so this is going to be infinity, right? This portion is going to be infinity, because the capacitance at a low voltage is 1 by JC omega, right? So omega is in the denominator out here. So initially at say DC voltage and close to DC voltage, this offers an infinite impedance, so there won't be any current. So this is current, so the impedance is very high out here, if you see here, right? Then slowly as the frequency increases, okay, this is the value of XC, and XL also increases, so the net slowly the net impedance also decreases out here, so the current will increase, it will keep increase, and it will reach a max value, okay, when XL minus XC is equal to 0. Okay, we'll do this derivation subsequently. What is the condition for this to be a maximum? Okay, so this will be maximum when the frequencies XL is equal to this gets cancelled. Okay, at that condition it will, that is known as resonance. In that particular condition, this will offer only a pure, it will work like a pure resistive circuit. Okay, whatever is the phase lag and lead generated by these two inductance and capacitance, it is L j omega is equal to 1 by j omega. See, so they get cancelled. If you see, go back and see the vector diagram out here, these two magnitudes, they become equal at that particular frequency. Okay, that is when omega 0 is equal to 1 by LC, right? At that omega 0 square is equal to, if you equate this, okay, it will be that frequency, right? So when these are equal, so at that XL is equal to, if you equate this, you will get omega 0 square is equal to 1 by LC. Okay, at that particular frequency, they will cancel out each other, and then the maximum current will flow into this circuit, and which will be given by V divided by R, plane R. Okay, and then in that particular case also the phase difference between the voltage and the current will be 0, right? So this is the phase formula is given tan inverse XL minus XC by R. So initially when the signal is, when XC is very very low, you will find XL is large, so it is tan inverse. So this term comes out to be positive, right? So if it is a positive, that means the current will lead here, because it is capacitive. It will work. It is more a capacitive nature circuit. So as and when the frequency comes to the resonant frequency, there will be no phase difference, and then if it keeps increasing again, now the inductance will start offering a greater impedance, right? At omega is equal to infinity, L omega will become infinity. Again the current will become 0. So this is the nature of the impedance. And the impedance will be exactly opposite, inverted of this. This is the nature of the current with respect to the frequency, how the current is going to vary as you keep increasing your frequency from 0 to infinity, and this is what happens with the phase of the circuit. Okay. So this is about a series RLC circuit. We take an example and make things little more clear. So a RLC series has a 40 ohm resistor, a 3 millihenry inductor, and a 5 microfarad capacitor. They are connected in series. Find the circuit's impedance at 60 hertz and 10 kilohertz, right? So that we learned that it is frequency dependent. This L and C are frequency dependent. So the frequency needs to be specified here. So in the question we are trying to find the impedance at two different frequencies, and if the voltage source RMS is given as an 120 volt, okay, what is the IRMS? Okay, so RMS is given as 120. It's not V0 like I told in the morning tutorial. V0 in this particular case will be the peak voltage, because this is a time domain representation. So VRMS is given as 120 volt out here. So first we need, at 60 hertz we need to find out what is XL, which is omega L, but nothing 2 pi f L. So frequency is given as 60, and 2 pi is 6.28, and 60 and 3. So it comes to be 1.13 ohm. Similarly, capacitance is 1 by 2 pi f C, right? It is 1 by omega C. So you have 2 pi 6.28 and omega, and C you get 531. So at low frequencies you will find the impedance offered by the capacitance is higher, and that offered by the inductance is lower. So when we try to compute it for 10 kilohertz, it will be the other way around. We can see that. So at 10 kilohertz, instead of 60, we use 1 into 10 to the power of 4, which is 10 kilohertz. When we do that, you will see the impedance offered by the inductance has greater, because L omega. So it is at high frequencies from 1.13 ohms, now it is offering 188 ohms, a higher impedance, whereas the capacitor, which was offering a high impedance at low frequencies, at 10 kilohertz it is offering at a much lower, because capacitor is going to almost act like a short circuit at a higher frequency. So this is how the impedances of the inductor and the capacitor look at these two frequencies. Now to compute the RMS current, we need to take care of this R also and find the total impedance. So the total impedance we know is given by R square into XL minus XC square. We are doing that for this is for 60, and this is for for the 10 kilohertz. Okay, so here there will be a negative, but we are presently bothered about the magnitude aspect. So the magnitude will be 531 and 190. So if I have to find the IRMS, it will be VRMS divided by Z. So IRMS is given as 120 here. So 120 divided by 531 for the first case, and for the second case for 10 kilohertz you have 120 divided by 190. So these are the two currents. Okay, but the thing which is not highlighted out here is this current will be an lagging current, whereas this will be a leading current out here, because if you see if you do the phase, you will find this is lagging and this is an leading. And also now how to compute the power in a series RLC circuit. Like for an we saw for an pure inductive and capacitive, the power was 0 because the current would flow exactly at 90 degree lead or lag with respect to the voltage which is applied. So hence we saw that the power was IRMS, VRMS, cos phi, which was either plus 90 or minus 90. Whereas for an resistance, we computed that in the previous class, that the power was IRMS into VRMS, because phi used to be 0 in that case, because the current and voltage will be in phase, and hence cos 0 was 1. So when you have an RLC circuit, so it is a case in between these two extremes. So the power will be computed as IRMS, VRMS and into cos phi. So the value of the cos phi needs to be computed by using this formula, R divided by Z. Okay, so cos phi. So we saw tan, right? Tan phi is x here. All right, at XL minus XC by R. So with the cos phi will be nothing but Z divided by R. If you make this triangle, okay, you will get the same equation. So you can do this R divided by Z to get the and equate it to cos phi also. Okay, so otherwise you can do the tan equation also. It is both are the same. So this is how we compute the power out here. Now when we see this is the active power, this is known as the active power, VI cos phi. Okay, this is the actual work that needs to be done by the source, and this power will be dissipated as heat in the resistance. Whereas this reactive power, okay, what is the reactive power is VI sin phi. Okay, there is this component also. What is this component is actually energy being transferred from the source into the inductor capacitor and pushed back to the source. So this is a kind of oscillating power. So this reactive power actually doesn't get dissipated as heat or something. This reactive power has come because of the inductor and capacitor. If there is no inductor and capacitor, these two power there won't be any phase difference, and apparent power and active power will be the same. Now because of this reactive power, so you have something known as an apparent power. So generally in a circuit we try and minimize the reactive power. Okay, because what reactive power does is, because ultimately the reactive power is of no use. It is just a oscillating power from the substation to our house and going back, right? There is no it is just an oscillating power, but then in the transmission lines this increases the magnitude of the current. So in the transmission lines excuse me, they are not ideal transmission line, so there will be some amount of resistance. So it will amount to I square R losses, greater I square R losses. So it is in the interest of everybody to keep this phase lag as low as possible. So if there are some compensation techniques available, where if there are huge inductors which are connected, then to compensate that you need to connect few capacitors also. Like if you have huge motors and all, they offer very large inductance, and they spoil your power factor. So in those cases capacitors are used to try and bring the reactive power as low as possible. Okay, so that is done in practical applications. So So if you are told to compute active power, reactive power and apparent power, so these are the formulas which you need to use. Okay, Vrms, Irms, cos phi. Okay, from the source side. Okay, so this is the voltage from the source, and Irms is also in this series circuit. So I is the same. So Vrms source into Irms source into cos phi. Cos phi is the angle between these two. So that will give the active power. That is the actual power drawn from the source. The reactive power drawn from the source is known as it is known as Vi sin phi. Okay, it is also represented by Q. Q indicates its quadrature. Okay, and then the apparent power. So the apparent power is nothing but a vector sum of these two powers. Okay, so so this is what happens. So if you take an analogy, this is the actual power. If you take this froth of a beer, and that is something known as reactive power. But then this total together becomes apparent power. So these are the formulas which we need to know to compute this active power, Vi cos phi, and apparent power will be Vi sin phi. The measurement is, this is watts, because this is what is power, right? Energy into time. This is watts. This is this represents the actual energy which gets consumed per unit time. So that is the reason this is this comes in watts. Whereas this is just an power being oscillated. So it is represented as, because it's an product of voltage and current, you write VA, volt ampere, and then we write R because it is reactive in nature, indicating it is out of phase. The voltage and the current are out of phase with each other. So this is VAR. Okay, so they are represented by Q. Okay, this. So we measure this using a wattmeter and this with an VR meter. So we'll see the measurement aspects also in the subsequent classes. Okay. So this is another problem which we'll just take on. It says for the same RLC circuit, in the previous circuit, having a 40 ohm resistor, 3 milliohm indicator and 5 microfarad capacitor, and voltage is same. It's the same problem. Now it says calculate the power factor and phase angle. Okay, for 60 hertz. Okay, and what is the average power at 60 hertz? Okay. So now we need to find out for the power. We need to Z we found out in the last case. It came to be 531. If I go back here, right, Z was 531. So this is the 531 from the previous example. So and this is the resistance value, right? So R divided by Z. So R is 40 ohms divided by Z. So you get this is the known as the power factor cos phi. Okay. So the 0.0753, this is at 60 hertz. So 60 hertz, and this is the and the phase angle can be taken found out by taking cos inverse of this value, which comes out to be 85.7%. So this is a very poor circuit where there is lot of inductive. So this has to be generally in a practical circuits, and this angle is kept somewhere between not exceeding 15. Okay, in practical real life applications, it is kept as low as 15. Okay. So now the average power is Irms, Vrms, cos phi. So this we found out in the previous example. So we just substituting the Irms, Vrms and cos phi value. So at 60 hertz, this is the power which we get. Okay. So you can do the same computation for 10 kilohertz also, right? And if you want to find out what is the power at resonant, the maximum power which will be pulled out from this circuit will be at resonance. Okay, at resonance means when L and C, L omega is equal to 1 by C omega. So in that particular condition, the only impedance which will be offered by these three in combination will be R. So if you have to compute, say if I tell you to compute what is the max power which will be consumed in this circuit, or from which will be taken out from this particular source. So we just have to take V RMS value, that is 120 V RMS square divided by 40, like V square by R. So the max power condition, and at what frequency, if I ask, then you got to compute the frequency by equating L omega is equal to 1 by C omega. Okay. So we'll again discuss that aspect in depth in lecture known as resonance. Okay. So this is what this we computed the power. This we did. Okay. Now I can also have an resistor and an inductor. So this is only a special case of RLC circuit where C is not there, okay, where a capacitor is not there. So R and C. Okay. Now if I make the phasor diagram out here, it is pretty simple. If the current is flowing in say X direction, so the voltage across the resistance will be in the same, and inductor will be and voltage across the inductor will be leading by EL, and the total applied voltage will be vector sum of these two voltages, ET, right. Now now if you have to find out the difference between the angle of phase difference between the applied voltage and the current which is drawn from the source, this will be the angle, right, and the current will lag here because it is inductive in nature. So the current is going to lag here. So this is going to be the current. So now this is going to be a tan inverse XL by R. So this is inductor, opposite side, this impedance comes from the XL, and this is R. So it is going to be XL by R. Initially we had XL minus XC, now XC is not there, so XL by R. So Z is equal to R square plus X square, this is the net impedance. So in this circuit, as the frequency keeps increasing, the current will keep decreasing, right, because it is an L omega. So here there is no resonance or something like that. If you keep increasing the frequency, the current will keep dropping because the impedance will keep increasing linearly in this case, right. In this, since there is an inductor, the current is going to always be lagging only. So there is no way the current can lead, because you have just a pure R and L in this circuit. So this is a series RL circuit. So if I take a problem out here, and RL circuit is made up of a resistor, value is given as 150 ohms, and inductor is 100 ohms. Okay, so already XL is given here. Okay, when I say 100 ohms, it means actually speaking, I cannot specify 100 ohms, right, because I have to specify L and the frequency. So if it is specified XL, that means it is understood that we are speaking about one specific frequency. Okay, so we don't have to worry about the omega part. This is XL. Okay, since it is given in ohms. Okay, so so don't no, if such a problem is given in exam, don't ask for frequencies. The L depends on frequency, so the value of frequency is not given here. Okay, so this 100 ohms is L omega, so that includes the frequency aspect also here. So now how to calculate the phase angle theta of the circuit. So this is the impedance is R square plus XL square. Like I said, XL is given as 100 ohms. So we just have to take the square root of these two. So you get 180 ohms, and theta is XL by R. So 37.7 degree. So the current is going to lag by this much amount, right? So this is how we write it in the rectangular form impedance, and this is in the polar representation. Right. So I will take one more of this problem. So here we have to calculate the value of the current flow, the value of the voltage drop across the resistor. Okay, calculate the voltage drop across the inductor, and calculate the phase difference. So the first step, like I said, is to find out the impedance. Right, we start by finding out the impedance. Here, yeah. Sorry, again here the impedance is given here, so you don't have to compute here. So straight away I can find out the current, which will be square. Now where did I get this 180 from? It is square root of 150 square plus 100 square. Okay, from there I can find out what is the current here. Is it understood? Kedar, where did I get this 180 from?
Yes, sir.
Okay, so this is a square root of these things, and now to once the current is known, what is the voltage across this resistor out here. So if you see, the voltage across the resistor is I into R. So once we found out the value of I, you can just do that. Similarly, I into XL is the voltage across the inductor, right? And then this is again applying the same formula. Similarly, okay, this is the total value of the voltage, and voltage across this is the voltage across the resistance, which will have no phase lag with respect to the current, and this will be 90 degree, and this is a total will be 33.7 here. So this is okay. One important aspect which I missed out is, let me go back to the RLC circuit. Yeah, here see, I may be applying say 220 volt signal out here, right? Is it possible that I get 1000 volts across the inductor? Yeah, Kedar. Yeah, in RLC circuits it is possible, right? It might be possible that you are applying a voltage, because if you see this and this, they get cancelled with each other, and then you can have like suppose this can be 1000, this can be 800, and they get cancelled, and then you have 200, and then you can have a resistance which is 100, which comes out to be, some of them can come to 200, right? So it is possible that you might be having an voltage of only 200, whereas the voltages across the L and C can go many folds higher. So you got to be really you have to take due precaution in your design. You have to be careful with your designs, because if you offer an low impedance with L and C, it can result in currents and voltages which are very high. Okay, the terminal voltages across these can be very high. So those high voltages can cause sparks. Okay, that when I discussed about inductor, we saw that spark could fly between the terminals of the relay. So same thing can happen in these kind of circuits also. It is possible that the voltages across the inductor and capacitor can go much higher. Okay, so for certain frequencies and for certain values of L and C, so you need to be careful with that aspect. Okay, this we saw. Also we computed this, and then this is the power in an RLC circuit. So this is the apparent power which is across the source, and this is the power across the resistance, will be known as the true power, and the power across inductor will be known as the reactive power. Okay, and the way to find out true power and reactive power is take this voltage and this current and into cos phi will give the true power, into sin phi will give the reactive power, and then the vector sum of those two will give ET, total power. So this is an in the same example you have 440 2.24 and then so you have a true power ER into IR. Okay, other way of finding out is you take this 440 into the current into cos phi, or you can just take the voltage across this resistance and the current, again you will get the same value. Okay, similarly in the inductive power is either you take this voltage into the current into sin phi, or you take the EL, what is the voltage across the inductor and current, you get this value. Okay, this is the power in the inductor. Captive power is not capacitive power. Captive power means the total power which is taken from here, which is root of this square plus this square. So that is known as the captive power here. So and power factor, this formula is, we know that this formula, right. This is power factor is watts divided by, this is also power factor. Another way of computing power factor will be that true power divided by the VA. Okay. So that will give you the whether it is leading or lagging. So this also can be computed, right. Again, series RC circuit, again this is also again a special case of RLC circuit where we don't have L out here. Now if you see, now there is a current which will flow here. This is the current, and the resistance, the voltage across the resistance, which that will be in sync with the current. Okay, they will not have any phase difference, whereas the voltage across the capacitor will now lag by 90 degree. Since the current in the capacitor leads, or in other way, the voltage across the capacitor is going to lag the current by 90 degree. So you put it down here. So now the phase difference, now the phase is going to be the current is going to be shown in the negative direction here like this. Okay. So it is -5, that means the current is going to lead. Okay. So you have this is the some voltage. So the equation gets modified accordingly. So you have z square is equal to r square plus x square, and tan phi is equal to xc divided by r. So xc is nothing by 1 by rc, right. So this equation gets modified and accordingly. For current, we have v divided by root of r square plus x square. So so things like, instead of L omega, it becomes 1 by c omega. So that's the difference which is going to come when we replace the inductor by a capacitor. So if you take an example out here, so you have a capacitor which has an internal resistance of 10 ohms and capacitive value of 100 microfarad. So so this is an internal resistance. So we have depicted it here as a resistance. Okay. So capacitances also can have some kind of internal resistance, leakage resistances, internal leakage resistance. Okay. So that is 10 ohms, which is connected to the sine voltage. Calculate the peak current into the capacitor. So this is the peak voltage out here, right. So we can divide this peak voltage by the total impedance in this circuit to get the peak current, and also construct the voltage triangle. Okay. Voltage triangle is nothing but the phasor diagram. So to find out the peak, so here, like, since it is given in the sinusoidal form, so that means this is the peak voltage. Okay, this is not the RMS, but this is the peak voltage. So we need to find out the impedance, and the omega is given here, right, because it is sine 314t. So that this becomes omega. So 1 by c omega, you can find out an xc. So the first thing is to find out xc, 1 by c omega. So you get a value out here, and then we find out the total impedance, which will be square root of r square plus xc square. So you get a total impedance. Now if we divide the voltage, peak voltage, by z, we get the peak current. So to get the peak current is just Vc divided by 33.4, right. Suppose in this instead of 100 sine this 3, if it is given that and source of 100 volts with omega equal to 314 is given, in that case you have to infer it that one, it's written 100 volts source, that means it is the RMS value. So in that, to get, if you divide like this, you will get the RMS value, and then to get the peak value you need to multiply it by root 2. But in this case it is clear this is the peak value 100. So we straight away divided by z, we divided by z and get the peak current out here, right. And phase angle, again we use the same formula, xc divided by r. Xc is 1 by c omega, which we computed, and r. So this is 72.6 leading. Okay. We are not taking the magnitude aspect here, we are straight away writing it is as leading out here, right, because we know it is an RC circuit, right. Otherwise it is 1 by j, right. So it will come, a negative would come here actually, right. It is, we are only speaking about the magnitude here, and we are directly writing the result as leading, right. Otherwise the impedance offered will be 1 by j. So that jj, if you multiply, there will be a negative there also, minus j out here, right. So that minus will come here, minus. So it will be a minus here, indicating that the current is leading the voltage. Okay. So this is 72.6 leading. Okay. So similarly, now we have to the next part of the question was to make the voltage triangle, right? So VR, okay, is the VR is I into R30, we make it like this, and the voltage across the capacitor is 95.6, that is I into XC, which will be 90 degrees to the this X direction, because the voltage and the current are in 90 degree out of phase for a capacitor, and the net voltage 100 is now here 100, 30 and 95, they are all the peak values, okay. So it is shown here, right? So the algebraic sum of this and this will come to be will come as 100. If you do that, then you will get 100 out here. So this is how we do it, okay. So that's all for today. In the next class, we'll see parallel circuits, RLC circuits, and followed by that, we will see resonance in RLC circuits, okay. So thanks a lot.